Okay, to summarize, what we have done so far is that we wanted to calculate, we were calculating this matrix element F and I, which is given by the path integral dx I to F, and then d lambda over the gauge volume and e to the power I by h bar s x comma lambda. And then we did that gauge slice fixing and all that analysis to get rid of the factor of v, and and we ended up having this expression. If this entire d lambda integral became an integral of dE 0 to 1 m of E, the measure, and then e to the power I by h bar s x comma E. A lambda is the entire lambda is a constant configuration E. So what we would do is next is to calculate this. Okay, so we did not explain how m has to be obtained, but we will skip that analysis. But in this particular case, this measure is 1, and so this is 1, and we will give a new name, this to be SE of x. Okay, so this is how, if you recall, this just a moment. This action was given, the relativistic action was 1 over alpha integral ds 0 to 1 lambda inverse x dot square minus lambda mu square. Okay, and now you set lambda to a fixed, lambda was a function, but now we have gauge fixed it to a constant value, and so this we will consider as a working formula with m equal to 1 as a working formula for this expression. Working formula for propagator is is xf, yeah, is integral dx I to f, then integral dE, which is the integration over the slice, gauge slice in sigma, and exponential I over h bar SE of x, where SE of x is given by 1 over alpha integral ds 0 to 1 over E x dot square minus E mu square. That is what you get after you evaluate that measure factor in the sigma space. This is the result that you get. Now, it turns out that you can eliminate E dependence. So E dependence in integrand can be eliminated by doing a reparameterization, which is S goes to S prime equals E times S, And under this, x mu of s goes to x prime mu of s prime, which is same as x mu of s. And then if you do that, then se of x prime, okay, in terms of x prime, it the action is given by 1 over e times alpha ds prime 0 to e. Sorry, so let me give you the final result instead of doing the calculation. Just straightforward thing. So it is given by 1 over alpha integral ds prime 0 to e x dot prime square minus mu square. And now using this, so therefore you can write as if I the 2-point function as integral dx I to f, then integral dE 0 to infinity e to the power I over h bar se of x, where se of x is 1 over alpha integral ds 0 to e x dot square minus mu square. This is the result you finally get. Now let us now evaluate it. Evaluate the path integral. And to do that, I will use the same technique that I did earlier, which is x mu of s is x mu lower bar, which is a classical function, plus y mu of s. X mu lower bar at s equal to 0. So now s has a range 0 to e instead of 0 to 1, because we have this done this reparameterization. So x mu of 0 is xi mu, and x lower bar mu of e should be equal to xf mu. These are initial and final. And for y mu of 0 is 0, and y mu of e is 0. And classical solution, x bar x lower bar mu of s is equal to xf mu minus xi mu, okay, divided by e times s plus xi mu, same as free particle, because it solves d to x lower bar mu d is to equal to 0. Substituting this, you end up getting the following result: if I equals integral dE 0 to infinity e to the power minus I e mu square by alpha h bar plus I over alpha h bar xf minus xi square over e times IE, where IE is the y path integral. Which is given by I by alpha h bar integral ds 0 to e eta mu nu dy mu ds dy mu ds. Now recall earlier result that c times f0 is equal to integral dy exponential I by h bar m by 2 integral dt di to tf y dot square is equal to square root m over 2 pi I h bar df minus di. However, that was in one dimension, one spatial dimension. That y was one spatial dimension. Here we have d space-time dimension. So for d space-time dimension, we have to do the following thing: double weak rotation, in the sense that in this case this t was sent to u, right? T was sent to just a moment. T was equal to minus IU. For okay, so for one dimension, what we did was we wrote t equals to minus IU. Now for d space-time dimensions, what you have to do is to so this is eta mu nu, so minus d y0 ds square plus dy vector ds square. Here you will not only have to write s equal to minus IU, but also weak rotate y0 to write y0 as minus I y0 bar. So these are double, because you are doing weak rotation both on the world line and in the space time. Otherwise, this world line weak rotation will take care of this oscillatory behavior, but then this y0 part has extra minus sign with respect to y vector part. So therefore, it will not be the action will not be positive definite, because the Euclidean action will not be positive definite. The Euclidean action was positive definite for a spatial coordinate. For a temporal coordinate, it has a wrong sign in the kinetic term, so it will not have. So you have to weak rotate y0 as well to make that positive definite. Then only the integral will will damp, and then do the calculation and we rotate back. So for D space-time dimension, need double weak rotation. Weak rotation both on worldline and in space-time. Yeah, that is this is the reason for that. After doing all this, using this result and also in D dimension, final result shows the final result you can calculate will be K xf xi, which is fi, given by integral dE 0 to infinity I alpha pi h bar e to the power minus d over 2 exponential I over alpha h bar xf minus xi square over e minus e mu square. And because of the translational invariance, one would expect the result to be dependent on xf minus xi only, right? That's what one gets. Okay, so we have calculated the propagator for the particle, for a spin zero particle. Okay, so that's for now.